This screencast is going to be about determining which reactant is the limiting reactant, or the limiting reagent, as they usually put it. The significance of the limiting reagent in a reaction as modeled by a chemical equation. The significance of the limiting reagent is that it controls how much product is made. Okay, it controls how much product is actually produced. It thus also controls how much of other reagents are used up. And the limiting reagent is the one, is the reactant that is completely consumed in a reaction. So it itself is completely consumed. So let's have a look at this. All right, so here we go. Let's look at this example, and it says, consider this reaction. And this reaction shows that we have some nitrogen gas and some hydrogen gas combining to form ammonia gas. This is actually a really important historical reaction called the Haber process, which is used to turn nitrogen into a useful form, ammonia, from the regular elemental form of nitrogen, which is in the air all around us. So it turned out to be important, but you don't have to worry about that at this moment. You'll just see it as an example a lot throughout the chemistry course. So the question says, if 0.6 moles of N2 and 2 moles of H2 are mixed, how much NH3 can be produced? And the key thing that's already been done here for us, but that we always need to pay attention to, is that the reaction is balanced. So it's already balanced. We would have a 1 in front of the nitrogen. We have a 3 in front of the hydrogen, and we have a 2 in front of the ammonia to make sure all the total number of atoms are the same on both sides of the equation, okay? And so there you have the balanced chemical equation. Remember that what the 1 to 3 to 2 ratio shows you is a mole ratio, okay? That means that we know if we're mixing these things together, we will need 1 mole of nitrogen for every 3 moles of ammonia, for every 2 moles, for every 3 moles of hydrogen to produce every 2 moles of ammonia we're going to produce. Okay, so that's the ratio. So the real question is here, like, which one of these reactants is going to run out first? Is it going to be the 0.6 moles of nitrogen, or is it going to be the 0.2 moles of hydrogen? Or are they both going to run out at the exact same time? Is it perfect amounts that we happen to have in our reaction vessel so that we're going to make a predictable amount of ammonia, or what's going to happen? So let's ask the question. Let's imagine here that if we use all of the N2, okay? If we use all the N2, so that's 0.6 moles of N2, how much H2 would we need? Okay, so let's complete that question by saying, how much H2, the other reactant, would we need? So pause the video for a second and ask yourself that question. Can you figure that out? So hopefully you realize to figure that out, we have to use these mole ratios. We have to use the 1 to 3 ratio, right? So if we're going to use 0.6 moles of nitrogen, the number of moles of hydrogen required for that is going to be times 3, right? Because you need 3 moles of hydrogen for every 1 mole of nitrogen. So if we were going to use all of the N2, we would need 1.8 moles of H2. And just to make sure you know whether you're multiplying or dividing, you're doing the right thing, I highly recommend you set it up this way so that your units will yield the units you want, moles of H2, right? So that's why I'm setting it up as a conversion factor like this. So what does it mean that we would need 1.8 moles of H2? Do we have enough H2 present in the reaction vessel to make this happen? And the answer is yes, we do. We have 2 moles of H2 present. So therefore, what would happen is all of this 0.6 moles right here would fully react, and it would use that much H2. We would have leftover H2, but we would consume all of the N2, okay? So therefore we would say N2 is the limiting reagent. Therefore, N2 is the limiting reagent. It's gonna run out first. It's gonna control how much product we can make. And that's because when we tried this test, it satisfied that test, okay? So now we can use N2 as the limiting reagent to actually answer the question that's been asked, which is how much N2 can be produced, all right? So we're gonna figure out how much N2 can be produced based on that amount of, how much NH3 can be produced based on that amount of N2. So scroll this up a little bit. If we wanna actually consider how much is properly gonna be made, we're gonna say we've got our 0.6 moles of N2. We know that we're gonna make 2 moles of NH3 for every 1 mole of N2. And we got that from the molar ratios, from the stoichiometric coefficients from the balanced chemical equation, the 2/1. Cross off moles of N2, we know we're gonna end up producing 1.2 moles of NH3. Okay? And that's your final answer. That's how much NH3 is going to be made. And it was determined by the limiting reagent. So the first thing was we had to figure out which one was the limiting reagent. Okay, here's another example. So in this one, we've got the reaction laid out there at the top. The chemical equation is written. If a mixture of 35 grams of CS2 and 17.5 grams of oxygen are combined, what mass of SO2 can be formed? Okay, so the first thing we should check is the reaction properly, I should say the equation, is the equation properly balanced? Okay, check if it's balanced. Don't rely on it being given in a balance. Don't ask me, is this balanced? Are they all going to be balanced? No, I don't know. You got to check. Are they going to be balanced? Count up the carbons, 1 on each side. Count up the oxygens, 6 on each side. Count up the sulfurs, 2 on each side. Yes, this is balanced. Okay, don't forget that step. Check if it's balanced. Next, because we're given random amounts of the reactants, CS2, oxygen, we have to determine the limiting reagent. Okay, determine the limiting reagent. And we're going to do it the way we did it for the last question. We have to use the mole ratios and kind of run a test and say, let's imagine CS2 is the limiting reagent. How much oxygen do we need? If that is satisfied, CS2 is the limiting reagent. Then we could ask the other way. If we use all the oxygen, how much CS2 are we going to need? Maybe oxygen's the limiting reagent. So let's figure that out. Once we figure that out, we'll use the limiting reagent to determine how much product, okay? To determine product created, or the product amount. Okay, we know what's created, we just need to know how much, all right? So let's go about this business. All right, just mix up my color here. Let's determine the limiting reagent. So again, we'll say if all the carbon disulfide, I guess it would be, if all the CS2 is used, so that would mean that it's the limiting reagent. Let's figure out how much oxygen we need. First, we are given masses, okay? So again, realize that those are masses because they're written in grams. So we can't compare mass to mass, right? We have to compare moles to moles. So let's first just transform that into moles. So the moles of CS2 is going to be equal to mass divided by molar mass, right? So how much mass do we have? We have 35 grams. A little bit. There we go. The molar mass of it, if you get the periodic table and you add 12, and then I think each of those is 32, it's around 76.2. Okay, so we know that there are 0.459 moles of CS2. All right, now how much oxygen is there? Let's figure that out. Again, same thing. We're going to do mass divided by molar mass. We know the mass of oxygen is 17.5 grams. We know the molar mass of oxygen is 32 grams per mole. We're going to get 0.547 moles of this. All right. So if we use up all of the CS2, all right, so 0.459 moles of CS2. How much oxygen does that require? Well, we once again have a 3-to-1 ratio. 3 moles of oxygen for every 1 mole of CS2. Okay, so that's going to be our little factor there. We're going to multiply that by 3. If you multiply it by 3, you get 1.38 moles of O2. Okay, so do we have that much O2? That's how much would be required to react. You know, if all the CS2 is consumed, that much is required. Is that going to work? Are we going to have enough? How much do we actually have? We have 0.54 and we need 1.38. So the answer is no. We don't have enough oxygen to react all of the CS2. So which one's the limiting reagent then? Well, therefore, oxygen is the limiting reagent. The oxygen would run out before we could react all the CS2. So when we do the stoichiometry of the product created, we have to use oxygen as the reference reagent here, okay? So let's carry on using oxygen as the limiting reagent. So now we're gonna say, let's use all those moles of oxygen, 1.547 moles of oxygen, and we're gonna answer this third part. How much product is actually created? So how much, which product are we after? We're after SO2. How much SO2 can be formed? Well, we have a molar ratio, so we're going to multiply that by the fact that you get 2 moles of SO2 formed for every 3 moles of O2 reacted. So we're going to multiply that value by 2/3. Okay? When we do that, we find out that we are in fact going to form 0.365 moles of SO2. Again, check your units, make sure you use the ratio with the correct numerator denominator. And that's how much we're going to get. The final thing is it says what mass. If you go back and look at the question, it's asking about what mass. So we need to convert this to a mass. Converting that to a mass, we're going to say the mass. Oh, did my pen get thicker? Guess so, whatever. The mass is going to be the moles times the molar mass. Okay, so we have 0.365 moles of SO2. It might be a little bit too thick, but we'll figure it out. Molar mass of SO2, if you look at the periodic table, put in 1 sulfur, 2 oxygens, you get 64.07 grams per mole. Do the math on that. And you get, it's 23.5 grams ultimately of SO2 produced. I hope that helps and makes sense to you in how you find limiting reagents and how you use limiting reagents to predict products.